In this lecture we want to link characteristic polynomial and minimal polynomial. So we start with the field extension L over K and say alpha is an element of L. So corresponding to alpha there would be a minimal polynomial, and let this f of x be the minimal polynomial corresponding to alpha. And in the previous lecture on norm and trace, we have associated with this alpha a matrix A alpha, which corresponds to the multiplication map from L to L. So going from L to L via multiplication by alpha, you can essentially use the matrix A alpha. So corresponding to this matrix, we have this characteristic polynomial, and corresponding to this alpha, we have this minimal polynomial f of x. So this proposition essentially says that the characteristic polynomial is almost the same as minimal polynomial raised to some degree m. So this is the characteristic polynomial, and characteristic polynomial is always corresponding to a matrix, and the matrix here is this A sub alpha, which corresponds to this alpha right here. And this m here, this is precisely this degree of extension of L over K alpha. So our extension is L over K, but this m is L over K alpha. So that is, you have adjoined this alpha right here, so that you get m. So before we start proving this theorem, let us recall Cayley-Hamilton theorem. So Cayley-Hamilton theorem says that the characteristic polynomial of a matrix A, this is given as like this. So this is just the notation first. So determinant of xi minus a. So this I is the identity matrix. So if this is your characteristic polynomial, then the Cayley-Hamilton theorem states that instead of x, if you plug in a, you get the 0 matrix. So this is a 0 in bold, so this is a 0 matrix. So first we study this case 1. So in case 1, we take the simplest possible case, that is m is 1. So L is K alpha. So our extension is K alpha over K. And this m would be 1 because we have K alpha over K alpha. So we have to show the characteristic polynomial is equal to f of x, because m is 1 in this case. So first note that for any alpha here, we are associating this matrix A alpha. And in the previous lecture on norm and trace, we have shown that there is an injective map from alpha to the matrix A alpha. And this map is a homomorphism. So what is it homomorphism from? It is homomorphism from L. So because this alpha is taken from L, so alpha is in L, to these matrices. And these matrices are nothing but ring of endomorphisms of L as a vector space over K, because these matrices take vector space L to vector space L, and these are vector spaces over K. So now the Cayley-Hamilton theorem says that this chi of A alpha would be 0. So essentially just copying this. So characteristic polynomial of A will satisfy this equation. So characteristic polynomial would satisfy this equation. So this is 0. And this implies that chi of alpha is 0. So this implication is not that trivial to show. So we will talk about this in a minute later. But assuming that this is true, so say this implication is true, this follows from Cayley-Hamilton, and then we have to prove this implication. Say this is true, then chi of alpha is 0. So that means that this chi of alpha is 0 means that alpha is the root of chi. Now but f is the minimal polynomial. So since f is the minimal polynomial, it has to be the case that f of x divides chi of x. If alpha is the root here, alpha is also the root of minimal polynomial, and minimal polynomial will divide every other polynomial. Now but both of them are monic, because characteristic polynomial is monic and our minimal polynomial is monic, and they have the same degree. So degree of f of x is obviously degree of our this extension here, K alpha over K, which I am taking as L is taken as K alpha. And a degree of characteristic polynomial, we have seen that this would be exactly equal to the dimension of the space, which will again be degree of this of L over K. So it is always degree of this extension L over K, because that represents the dimension of the vector space, because your matrix will be of the same dimension. So if this dimension is n, our matrix would be n by n, and therefore the degree of the characteristic polynomial would be n. So here we are taking L as k alpha again. So degree of both these are the same, both of them are monic. So if f of x divides chi of x, both of them are monic, both of them are the same degree, it has to be the case that f of x is equal to chi of x. Now the only thing left is to show this implication. So say you have some polynomial f of x like this. So this is not our minimal polynomial. So this is just some polynomial. So this is just some polynomial, which is not necessarily the minimal polynomial. So this some polynomial is given to us. So we are going to plug in a here, and because our characteristic polynomial is just some polynomial, so we have to show that this implication would hold. So this is some polynomial. So now for these matrices a alpha, if you multiply with the constant, this is a c alpha. A alpha times a beta is a alpha beta. A alpha plus a beta is a alpha plus beta. So these are all the small things which come from associating. From alpha you get a alpha, this map here, and from beta you get a beta. So corresponding to any such alpha or beta in L, you can form the corresponding matrices, and these properties will be satisfied by these matrices. So now instead of x, put in a alpha. So you get we're just putting, instead of x we are putting a alpha, but now we can use this property. A alpha times a beta is a alpha beta. So you have a alpha to the n here. So this is the constant here. This constant will come inside because of this logic here, this equality here, and then you are multiplying. So you get cn minus 1 alpha n minus 1 and so on, and then you can multiply. The multiplication comes inside, and then you can add them. So a alpha plus a beta is a alpha plus beta. This becomes like this, and this becomes this map. So now same thing will hold for characteristic polynomial. Now this thing is 0 if f of alpha is 0, and that is precisely because we had an injective map. This map corresponding alpha to a alpha was an injective map, and this map will assign to 0, it will assign 0 matrix. So if you have a 0 matrix, that would mean that this element to start with was 0. So that means f of alpha would be 0, and that's what we wanted to show right here. So because characteristic polynomial is just some polynomials, and we are writing f in place of it. So don't confuse this f with the minimal polynomial f here. So now we talk about the general case. So in the general case, let beta 1 to beta n be the basis of this k alpha over k, and gamma 1 to gamma m might be the basis of L over k alpha. So then you can say beta I gamma k, where I goes from 1 to n and k goes from 1 to m, is the basis of L over k. So this is precisely like in Galois theory, when we construct a field extension and we construct another field extension on top of it. So this is the basis we get. So now recall that any matrix A, it can be recovered by its action on standard basis. So you can think of matrices on real numbers and action on our standard basis of Rn. So E1 would be 1, 0, 0, 0, and so on. So the ith column of this matrix you can write as AEI is just the summation j equals to 1 to n AJI EJ. So now this looks complicated. This matrix A is given by Aij. So our matrix A here is given as something like this, Aij. But notice that we have AJI here. So this might look complicated, but we can immediately see an example. So say you want to recover the first column. So the first column of the matrix you can see as A11 times E1 plus A21 times E2 all the way to AN1 times En, the basis element. So for example, you can just consider this matrix A in real numbers and these bases in Rn. So n by n matrix on real numbers, and you want to recover the first column. So you just take this sum A11 times 1 0 0 and then A2 1 0 1, this column of this thing, and so on. So you will get the first column. So this is important. So this is how it is represented. As you can say that this this 1 here, this j is changing with this j. So 1 is changing with 1 here, this 2 is changing with this 2 here, this n is changing with this n here. The second is constant, so I is not changing at all, so this I is remaining same as such. So this is how you got the first column. So the first column is AE1, and this is the one over which we are summing up. So we are summing up over j. So we are summing up over this first index. So as you can see, so this is important because we are going to use this formula in a minute, and as you can see how you can recover the first column using this formula. So again, this A is Aij is the matrix. It represents multiplication by alpha, as we have said before. So to alpha you're representing A alpha, we're just putting A here. So now you have alpha beta I, you can write in this form. So now our basis is all these vectors beta j. Instead of ej we have this basis here, 1 to n. So j goes from 1 to n. So all these bases, again this I am copying right here. So any element like this you can write in terms of basis. Now you multiply both sides by gamma k, you have gamma k here. So now we have this basis here, so I'm going to write it in full expansion. So you have beta 1 gamma 1 beta 2 gamma 1. So this is corresponding to gamma 1, and all the betas, this is again beta 1 gamma 2 beta 2 gamma 2 all the way to beta n gamma 2. So you can see there are m rows here. So for the simplest possible matrix A, so say we have identity matrix, this you can multiply with our basis. We just had basis beta 1 beta 2. So nicely you will get something like this, beta 1 beta 2. But now we have increased the basis, we have adjoined gamma 1 gamma 2 also to it, but now we need 4 things. We need this matrix, so now we need this. So we have repeated this matrix twice. So say this matrix is A, you have this here and then you have this here. Now you can multiply it with say your 4 bases, which is beta 1 gamma 1 beta 2 gamma 1 beta 1 gamma 2 beta 2 gamma 2 to get a different matrix. So this matrix A has been repeated twice here. Once it is here, then it is here, everywhere else it is 0. So here corresponding to gamma, here we are joining 2 gammas to it, gamma 1 and gamma 2. Here we are joining m gammas to it. So this matrix A will get repeated m times. So our corresponding matrix would look like this, where this bold 0, these bold zeros are nothing but 0 matrices. So we have to take characteristic polynomial of such a matrix. So if you try to find characteristic polynomial of such a matrix, that will just be determinant of xi minus a to the power of m, because there are m such matrices on the diagonal. So that's why you have power m here. So you just compute the characteristic polynomial of a single matrix and raise to the power of m. So this is chi of x to the m, but this we have just shown to be equal to f of x. So this becomes f of x to the power of m. So now we will do an example which will use this proposition. So we will have a field extension L over K, alpha will belong to L, f of x would be the corresponding minimal polynomial. So this should be minimal polynomial corresponding to alpha, and then we have the characteristic polynomial corresponding to alpha. So this alpha is nothing but a matrix here. Now we are thinking of matrix A alpha, and then you have this m as the degree of this extension. So now let us consider this field extension which has 2 to the 1/8 and this complex I, which is square root of -1, adjoined to rationals over rationals. Now this will have degree 16. You first adjoin this square root of -1, which will be degree 2, and then you adjoin 2 to the 1/8, which will have degree 8. So 2 times 8 will give you 16. Now this is precisely the splitting field for this polynomial x to the 8 minus 2. So now we will write 2 different examples. So in the first example, you take alpha as 2 to the 1/8, you take field L as this 2 1/8 adjoined to rationals and k as just rationals. Now then m is L over k alpha. So but alpha is 2 to the 1/8. K is rationals, so K alpha is rationals 2 to the 1/8. So this we are copying here, and L we are putting this like this. So M is just 1 now because L is same as K alpha. So if M is 1, the characteristic polynomial corresponding to alpha, which is 2 1/8, this is our field extension L over K. So L over K will be just the minimal polynomial. So minimal polynomial for 2 to the 1/8 is x8 minus 2. So this is the minimal polynomial for our alpha, which is 2 to the 1/8. Now you know that if your characteristic polynomial is given like this, you expand it. This term here is a trace, and the constant term here is the norm. So there is no term with x to the 7. So this is xn minus 1. So there is no term x to the 7. So the coefficient of x to the 7 is 0. So the trace is 0 and norm is minus 2. So notice that how easy it is to compute here. Otherwise, since this had degree 16, we would actually require a 16 by 16 matrix to compute trace or norm. Here through characteristic polynomial we are just computing straightforward. Now example number 2, alpha remains the same 2 to the 1/8, but now we are changing L. We are join this complex I to L. So this is our L, and K just remains as rationals. So now we have to determine this M. So you have to write K alpha here. So to K you join this 2 1/8, and L has this complex I. So now you know that to go here you have degree 2 because of the square root of minus 1. So M is 2. So now our this term here comes down here. So this is alpha, this is L over K. So this is x to the 8 minus 2 square. So square here. Again our alpha remains the same. So our minimal polynomial is still x to the 8 minus 2. And that's precisely why we square the minimal polynomial here, because this M is 2. So when you expand it, again there is no coefficient corresponding to x to the 15. So here you will just get x to the 16, and then you will get minus 4x to the 8 plus 4. So there is no coefficient corresponding to x to the 15. And this trace comes from x to the n minus 1, and n is 16 in this case. So trace has to be 0. And norm is this last term, so it is 4.